It's about condition-based monitoring of a turbine. The turbine is an important asset, and monitoring its health is critical. For this turbine, we have a sensor for the oil temperature. And the plant experts want to define a dynamic tolerance corridor to generate early warnings whenever this oil temperature doesn't behave normally. So we have to model the normal expected oil temperature. Here in this image, we see 4 years of oil temperature measurements. And the challenge is direct modeling is not possible because large parts of the data don't refer to normal operation. For example, a maintenance period in here, shutdowns and ramp-ups of the turbine are also not a normal state we want to model. And also after the maintenance here, the normal operation was different, meaning the blue part is not relevant anymore. And all this knowledge is only known to the domain experts. Only they can carefully select the data that is relevant here and then continue with the modeling. And this I would like to show you now in a live demo. So let me switch here. Yeah. So what I have started now is our software Visplore. It's a tool for data analysis tailored to power generation and distribution use cases. You can load your data from many sources here. In this case, I will load a CSV file, but databases, Python, etc. are additional options. Now I load this data set from the turbine. And you see here, it's a time series data set in 4-minute resolution over 4 years. And then you have all these values that are recorded. Okay, you see that I have loaded a table with 500,000 records now, approximately. And one special thing about Visplore is that you can start right away with one of our predefined analysis tools that you see on the left side here. Yeah, so without any configuration necessary, you can directly start one of these tools. In this case, we want to use a tool for multivariate regression. Now we have to tell the system what the target variable is. In this case, the oil temperature, and the rest are all independent variables. And with this, we can start right away. Let's begin by looking at the target time series, the oil temperature that you've just seen before. This is the oil temperature that you want to model during normal operation. Please ignore the plots on the left side for now. Let's not focus here. So we have 4 years of data here. Not all of it is normal operation, and therefore not all of it is useful for modeling. So this is the renovations period. I've shown this before. And during this renovations period, the system was also changed. So if you want to predict the future, only the time after the renovations is relevant. The experts know this, but it also becomes evident if you look at, for example, another input time series here, like this turbine flow temperature. You see this is how the system should behave. Like the variables should be very similar, and this was like it was before. So you see, after this renovations period, we can use the data for predicting the future. Back here, it's kind of obsolete. And yeah, we can do this just by selecting the time period here that you want to keep. Like in a drawing program, we can just select this data and then set a filter to only continue working with this. Right. So we see here some parts of normal operation, but we also see, and this becomes better visible when I zoom in, that there are also some shutdowns and some ramp-ups of this turbine. And this is also not the normal operation that you want to model. We want to model this rather smooth state here. And to select this, in this case, I can do this also again graphically by selecting some of these regions. I'll just focus on a bit longer ones now. Here, where it was part of the normal operation. Okay. Just have to be exact now for the demonstration and just keep these. Right. And now we have mostly periods of normal operation with some gaps in between. This is okay. We can also in this visualization collapse the gaps so that gaps don't take so much space. See, yeah, maybe like this. Now we see a nice time series of data that we can use. We still have one more thing here that's a bit disturbing, and these are these small spikes here. And these are actually interesting because they occur during normal operation, where the oil temperature makes such a pattern. And this could actually be something that we want to detect with our dynamic tolerance thresholds. So what we can do here is we can just select them and label them directly in the software. So let's just label this as unknown ramp, whatever. Okay. And then by scrolling through the data, we find the next and can easily, with one click, label this data here. There are a few more. Just repeat this for the two here. Here's one unknown ramp. Here is an unknown ramp. And I think the last one is here. So actually, data labeling is also something that you can do here along the way. When we zoom out, we see here that we have our label and can highlight this in the visualization. These would be instances that our tolerance threshold that we model actually should detect later on. All right, now let's look at some input variables. And here on the left side, we see a list of the input variables. And this list is actually ordered in a way that those that are most useful for modeling this target variable are ranked to the top. So here, for example, we have the water temperature, okay, which is ranked to the top, and we can actually look at the direct correlation between the two and see here, for example, that we have on the x-axis the water temperature, on the y-axis the oil temperature, and we see by now this looks like a quite nice relationship already. However, what we also see is that we have two clusters in here that wouldn't expect at this point. And to find out what the clusters are made up from, we can select one of the clusters here with a lasso, for example. And then, for example, look again in the timeline. And then we see, aha, this corresponds mainly to this period here in the beginning after this maintenance. Also, with the water temperature, this looks a bit different in the correlation. So maybe this is also a part that we want to exclude because, yeah, maybe it has had to calibrate sometime after this maintenance, or for some other reasons it's a bit different. So let's go back here and filter this out and focus only on this part. And right here we can actually switch on a visualization of a regression line, maybe not only linear but quadratic. And then we can see that this relationship, oil temperature from water temperature, is actually something we can model quite nicely once we have selected the data. And even the dynamic tolerance corridor becomes quite evident here, because you see that roughly around 1 degree degrees Celsius around this regression line is normal. And then you have these unknown ramps here that you see, which would actually be detected by such a rule. If you say more than 1 degree apart from this prediction should be detected. Okay, and we can actually do the modeling here in the tool. For this, I also filter out these unknown ramps now because I don't want to use them as a training data. So let's exclude them as well. So we have really clean training data. Okay, again, maybe a word on the list of input features here. This list here is ordered in order to help us select the useful features. We've heard today that feature selection is a challenging problem or a challenging topic in itself. And this list basically is ordering the features to help us choose those for the regression that have the best or the clearest relationship with the target variable, even nonlinear relationships. Water temperature is top ranking, and so this algorithm guides the domain experts towards the features that they can use here. If you're interested, the metric behind this just looks for each feature if the local variation of the target variable is smaller than the overall variation, because then this input feature tells us something about the target. This makes it also detect nonlinear relationships, like for example here, if you take the month, but actually the temperature is more useful here. And now we can actually model this here in the tool. So we can say we want to create a new regression model using the input water temperature. And by doing this, we have got a polynomial regression model here. You see the graph of the model here. You also see the model definition down here. So basically we have a polynomial up to 4th order using the water temperature with these coefficients. This is quite nice, but you see that there is also still some variance left in here that is not explained by the water temperature. And for this purpose, this list on the left here has updated now to help us find features that can explain the remaining variance. And now you see top ranking, for example, is a feature here called turbine part 2 position. I'm not completely sure, but I think it's a mechanical feature of this turbine that also, as you see here, explains some pattern that is in the errors of this model, which tells us we might gain something by including this in the model definition. So let's add this feature, make a new model variant that is 2-dimensional, based on the water temperature and this turbine part 2 position. And now you see, as in the slides, you basically have a visualization here of this 2-dimensional model, where again, we could do a what-if analysis and see, okay, if the water temperature is higher, how does it then depend on this second feature, for example? So we have our two models here. The first one had only one feature, the second one has two features, and we can see here that the RMSE has gone down, for example. And it's actually quite quick to end up here with an explainable model of this oil temperature here. Maybe also just one thing, we have these unknown ramps here that we had excluded, so maybe let's include them again in the visualization and look at the actual prediction that we have made here as a time series. And you see here now, our prediction time series is in blue and the measured values are in black. And you would nicely see that these unknown ramps that we have in here are quite strong deviations from our expected modeled behavior. And by defining a threshold here, for example, like 1 degree or a bit more, these would actually be able to be recognized for condition-based monitoring, for example. And when you have trained such a model, it's also possible to export it here as a Python code, for example. So you see here the formula with the coefficients and everything, which you could copy to the clipboard if you want to continue working with this, for example, in a Python environment. Okay, this concludes the live demo of this use case. Let me jump back to the presentation. To summarize, what are the results here? After selecting the useful data based on the domain knowledge, we now have an explainable model as a basis for dynamic tolerance bands. If we compare this to a static tolerance threshold that wouldn't depend on other variables, this allows the experts to detect the deviations much earlier. And what this example also nicely shows, the explainable model is just a part of the whole story. Without the domain expert carefully selecting the relevant data upfront, the modeling would not have been possible. So it shows that the human input is necessary in multiple steps here.